just like with substitution reactions where we had to talk about alcohols specifically, we have to talk about them specifically here for eliminations as well. Now, why do we single out alcohols as opposed to other functional groups? Well, it's two reasons. Number one, the hydroxyl group OH is generally a poor leaving group. Now, that by itself isn't enough of a reason to make us single it out. There's many other things that are poor leaving groups that we're not going to spend any significant periods of time talking about. So why alcohols? Well, as you're going to see starting in a couple weeks, we're going to spend about half of this course on carbonyl chemistry. Reactions of ketones, aldehydes, esters, amides, carboxylic acids, anhydrides, and acid chlorides, just to name a few. And it's reactions of these functional groups that is fundamental to a lot of what we do in organic chemistry. Well, the issue is most carbonyls can easily be converted to alcohols. Whether this is regardless of what kind of carbonyl this is, ketones, aldehydes, esters, etc. And it's usually a very straightforward reaction. Some sort of hydride type reagent will do this reaction. And you may recall that we may have done a lab like this in Organic 1. Part of our chromatography lab was we saw that we could very easily reduce this compound, fluorinone, to this alcohol, fluorine, using sodium borohydride. So, in other words, these reductions of alcohols, the fact that we can reduce alcohols, as well as we'll learn in our next chapter, there's many ways to oxidize alcohols into aldehydes, ketones, and carboxylic acids. Once you've got the carboxylic acid, that allows you to make any of the other functional groups, esters, amides, anhydrides, acid chlorides, and so on. So the first piece of this that's important is we're able to very easily interconvert alcohols and carbonyls. And the reason that that matters is that carbonyls are generally very good for forming carbon-carbon bonds. So if you think about some complicated organic molecules, oftentimes the most complicated piece is to make the carbon-carbon bonds. And we've seen an alkyne reaction that will let us do that. We've seen a couple other reactions here and there that let us make carbon-carbon bonds. But when it comes to carbonyls, just off the top of my head, here's 9 examples of carbonyl reactions that let us form new carbon-carbon bonds. And we can keep going. And so on. So we will spend a lot of time learning about reactions of carbonyls. Again, because they are so generally useful for making, building up structures. But sometimes we don't need that oxygen in the final product. We either need to substitute it away or eliminate it. And so that's why these reactions of alcohols are so important. If the alcohol is a bad leaving group, it becomes very difficult to get rid of. But if we can eliminate an alcohol, then we could use one of these reactions we've got named here, or any number of other reactions, and then very easily get rid of that alcohol and make it into something else useful. So how do we dehydrate an alcohol? Could we use acid to protonate? So the problem with using acid is that the type of acid you need to protonate an alcohol is going to be a strong aqueous acid. And that means you're looking at a protic solvent, water, and you're pretty much stuck with E1 conditions. So you can attempt to dehydrate an alcohol. And the reason we call this a dehydration is what we're removing from the starting material is a hydroxyl group on one carbon and a hydrogen on the other carbon. So the net result is we're losing water. Now, if you do this with a tertiary alcohol, it's pretty easy. Works quite well. You add a little bit of acid, you stir it for a little while at room temperature, and you get your E1 to take place. But if you try this with a secondary alcohol, less stable carbocation, and so you need stronger acid, maybe 75% sulfuric acid, and you're going to have to heat it up to 100 degrees Celsius, and you can get your elimination to take place. With a primary cation, even worse. You've got to hit the molecule pretty hard, pretty much pure sulfuric acid, high temperature, and you can get the elimination to take place. Problem is, conditions like this aren't really compatible with most functional groups. And so you have to be very, very careful if you want to try and do it this way. So the problem with dehydration of alcohols is that you need either strong acid and heat, or you need a OH minus as the leaving group. So what we showed on the previous slide will work fine for tertiary alcohols. But what do we do for primary or secondary alcohols? Well, it's something that's at least slightly similar to what we saw for nucleophilic substitution. Next, we add a reagent known as POCl3. Along with this compound, pyridine. Pyridine is a benzene ring where one of the carbons has been replaced by nitrogen. And basically, it's a weak base. So what happens in this reaction is that the alcohol attacks the phosphorus and pushes electrons up onto oxygen. This phosphorus is a very, very good electrophile. Why? Well, this phosphorus is bonded to 4 highly electronegative elements, the oxygen and 3 chlorines. That makes it a very good electrophile. That negative charge on oxygen adds back in, reforms a double bond, and kicks out chlorine. And then, at some point, we lose this hydrogen. So at this point, what have we done? Well, we've turned the alcohol into a good leaving group. And so our base, the pyridine, which I'll abbreviate here as PY, can trigger an E2 elimination reaction. And this leaving group we formed here is much more stable due to the resonance of this other oxygen. So it's a much more stable leaving group. And you can see here in this step that this is an E2 elimination. Everything's taking place at one time. So it's going to work well for primary and secondary alcohols. So in many ways, this is very similar to what we saw with substitutions. We had to do something that would make the alcohol into a better leaving group. Now, where might we run into a reaction like this? Well, as an example, anytime you start to see these carboxylate ions, the carboxylic acids that are missing a proton, it's probably a safe assumption that we're dealing with a biological process. And if that wasn't evidence enough, once we get the names of these enzymes up, we'll know that for sure. So we have the alcohol and the hydrogen, alcohol and the hydrogen. And if we remove those, we can get our elimination to take place. Both of these are steps that we find in metabolism.